Hello everyone, my name is Kathan and today we'll be discussing the problem coin piles from the Introductory Problems of the CSES Problem Set. Let's begin. Let me read out the question for you. So the question is pretty simple. You'll be given two piles containing A and B coins. So you'll have two piles of coins. One will have A coins and another will have B coins. On each move, so there is a move defined, you can either remove one coin from left pile and two coins from the right pile, or two coins from the left pile and one coin from the right pile. In a way, you can subtract either 1, 2 or 2, 1. Right, so either you remove one from first pile, two from second pile, or vice versa. A task is to efficiently find out if you can empty both the piles. So in a way, just by performing this move some number of times, if you can make sure that both the piles are left without any number of coins, right? So more concretely, in the first input line, we'll have integer t. So there will be some test cases given here. And after this, there are t lines, each of which has two integers a and b. So what will be the number of coins in the first pile and number of coins in the second pile. For each test case, we have to output yes if we can empty the piles by the moves that we have defined, like that is subtract either 2, 1 or 1, 2, and no otherwise. Like if you cannot empty the pile, then you print no. Constraints are given here, you can see. So test case can be as high as 1e5 and a and b can be as high as 1e9. So pretty high constraints, right? So I'll touch upon this in the discussion. And examples are given. So for example, here you can say this is 3 number of test cases will be given to you, and 2, 1. So you can just remove 2 from first pile and 1 from the other pile. So yeah, of course, yes, in just one move you can empty both the piles, right? Similarly here, like first you remove 1, 2 and then you remove 2, 1, or vice versa, 2, 1 or 1, 2, and then you will be empty the piles. So yes, here you cannot remove, like you cannot empty the piles, because like if you perform first move, one pile will be empty and another one will be left with 1, right? So either you perform subtract 1, 2 or 2, 1, you will be left with 0, 1 or 1, 0. So then you cannot empty the coin pile, right? So the test cases are pretty self-explanatory here. But let's go to the iPad and discuss the approach of this question. First things first, let's talk about the constraints here, because they're pretty high and it gives a hint like in what direction to think, right? So you saw that the test case input was as high as, maybe let me just write it below. The test case input was as high as 1e5 and a and b were as high as 1e9. They're pretty large inputs, right? So it says for each test case, even if you just try to, you can say, iterate through all the values from 1 to 1e9, maybe if you were thinking to simulate the process of subtracting 1, 2 or 2, 1, what will happen is the total time complexity will become 1e5 into 1e9, like if you were to simulate the algorithm, right? 1, 2, 2, 1 something and so on. So eventually you'll have to assume that in one operation you'll be able to reduce by just 1. So even like if you think about the brute force of simulating the algorithm some way, you will be having 1e5 into 1e9, which turns out to be 1e9, 1e14, right? So this is a very high complex, high time, right? So 10 power 14, you cannot do this many number of operations in 1 second. So this is not gonna work. You'll have to come up with something better, right? So if you cannot just go from 1 to 1e9, in other words, if you cannot do some order of n, or you can say order of a or b number of operations, what is the next best? It will be either log n or constant time. And turns out in such questions, there will be some sort of a math trick involved. So I'm not telling you to remember this anyway, but if you're not able to traverse it once, then either it will be log n or simply order of 1. So let's just see. Let's approach the question step by step and see if we can figure something out. Now, what we want is you have two coin piles. Like you have two coin piles. First will have A number of coins and second will have B number of coins. Now what you want to do is you have either two options, either subtract 1, 2 from it or subtract 2, 1 from it. In the sense, either remove one coin from the first pile and second 2 coins from the second pile, or remove 2 coins from the first pile or remove 1 coin from the second pile, right? So eventually can you reach 0, 0 is the question, right? So maybe you can spend some thinking about it, like how are you going to reduce it effectively. Of course you cannot linearly do it, like you cannot of course traverse all the possible paths here, right? You might be thinking, okay, let's just first try this, then maybe try two more and so on, see if we can reach 0, 0. Similarly you can try two options here, but it's not going to work, because this you can clearly see it is branching out to be sort of you can say exponential solution, right? Because in every branch you are spanning out 2, so it will be somewhat 2 power n solution. So let's not go in this route, like you cannot simulate the algorithm, you know, from the constraint, so better not think about that, right? So let's think something better then. See, what happens in such questions is, this is sort of, you can say, games related questions, right? So you have been given something and you have given some moves and you have to do something to eventually achieve a final state, right? So okay, I have AB and I have to reach some way 0 0. So if I'm not able to think, so either subtract 1 2 from it or subtract 2 1 from it. If you're not able to think from left to right, maybe try thinking in other direction, right? If you cannot do this, if you cannot go from, like, if you cannot think about logic of how are you going to subtract again and again to reach 0 0, maybe think in other order. Maybe let's say you start with 0 0 and by applying some number of, you can say, additions of 1 2 or additions of 2 1, can you reach AB, right? If you are gonna remove something and reach here, it is same as asking, can you add something here and reach here, right? So one the same thing, right? So this maybe simplifies the thing a bit. So now your question is, you start from empty piles. Can you reach AB? Can you reach AB by applying these type of moves? That is, add 1 comma 2 or add 2 comma 1. Can you do that is the question. For now, let's assume we can do it. In the sense, if we can do it, what it says is, you start from 0 0. You start from 0 0 and you can reach AB. So you can reach number of coins in first pile to be A and number of coins second pile to be B. So what are you gonna do is, you are gonna apply, let's say, 1 2 here, 1 2 here, 2 1 here, so anything, right? So by applying some number of 1 2 2 1 1 2 2 1, so on and so forth, you will apply some number of 1 2s and 2 1s. That is what applying 1 2 and 2 1 means is, add 1 2, add 2 1, add 1 2, add 2 1, you will be able to reach AB. So what you're doing is, we are assuming that we can reach AB from 0 0, right? So that's what I assumed, that my answer exists and I can reach from 0 0 to AB. Fine. So if that can be done, you will apply some number of 1 2s and 2 1s to reach it. Now just think a little bit. You will apply some number of 1 2 2 1 to reach AB, right, from 0 0. Can I just say, the order here doesn't matter. In the sense, if you start from 0 0, if you're applying some number of 1s 2s, in the sense, you're applying some, let's say, 1 2 2 1 1 2 2 1, it is same as applying some number of 1 2s followed by some number of 2 1s, right? Because, like, effectively you will apply some number of 1 2s and some number of 2 1s. Now the order really doesn't matter. So instead of just looking at them in a jumbled manner, like 1 2 2 1 1 2 2 1 or 1 2 2 1 so on, it is same as you will apply some number of 1 2, that is, add 1 to first pile, add to the second pile, followed by some number of 2 1, that is, add to the first pile and 1 to the second pile, right? So this can be seen. Now let's just call these many moves as X, right? So X number of 1 2 type of moves and Y number of 2 1 type of moves, right? Now if a valid answer has to exist, that is, if you are actually able to reach from 0 0 to AB, what it has to happen is this thing, X plus 2Y has to equal to A, right? Simple. Similarly here, 2x plus Y has to equal to B, right? So you are applying some number of 1 2s followed by some number of 2 1s. I'm just calling them as X and calling these as Y. So it says X plus 2Y has to be equal to A, of course. 2x plus Y has to be equal to B, of course, right? So what does it say? If you were able to actually reach AB from 0 0, in other words, you were able to empty the piles, a valid solution has to exist of these equations, right? The question is done and dusted. And what is a valid solution of this equation? Of course, X and Y has to be positive, like non-negative, right? You cannot apply, you can say, negative number of 1 2 moves or negative number of 2 1 moves, so that's obvious. If a valid solution for this exists, you can empty the piles, right? That is, how do you empty the piles? First apply these many number of 2 1s followed by these many number of 1 2s, reverse, right? Fine. So but for that, a valid solution to this exists. So what is a valid solution? Of course, the X and Y that you get from here should be non-negative and they should be whole numbers, right? Whole numbers, or you can say integers. They have to be integers. Why I'm saying whole numbers is because they have to be positive as well. That's why I'm just calling, like, if you remember, there was a natural number set and there was whole number set. So that's what I'm talking about. XY has to be of whole number set. Fractions are not allowed. So how do you check it? Like, if you want to check it, it's pretty simple. XY can be non-negative checked very easily. For the whole number check, what you can do is, maybe let's just call this as equation 1 and call this as equation 2. Now, if you call this equation 1 and 2, what I'll do is, guys, let's just multiply this first equation with 2. Let's just multiply first equation with 2 and subtract from the second equation. This is like an elementary mathematics I'm doing, right? So then it will give you 3y equals to 2a minus b, right? 3y equals to 2a minus b. Now, if y has to be integer, this thing has to be divisible by 3, right? Firstly, this has to be positive, or you can say non-negative if it has to be a whole number. Like, you need the values to be non-negative, right? So here the two conditions are there. Firstly, this 2a minus b has to be greater than equals to 0, and this 2a minus b has to be, you can say, divisible by 3. So these both conditions has to be followed, right? Similarly, like, once you get y here, what you can do is, if you got the y, then you can use this equation, right? You can use this equation, and then x will be what? 2x will be b minus y. So if a valid y exists, then you first need to check whether this thing is non-negative, right? Because they have to be non-negative. And if it is non-negative, is this divisible by 2 or not? So again, two cases, like, both the conditions have been satisfied. This b minus y has to be greater than equals to 0, and this b minus y has to be divisible by 2, or it has to be even, right? So the question is actually done and dusted. What we were after is, from AB, can you apply some number of 2 1s or 1 2s to reach 0 0, right? But instead of thinking in that direction, we thought reverse. Can we reach from 0 0 to AB? And we assumed yes, we can achieve that. So if we can achieve that, there will be, of course, some number of 1 2s followed by some number of 2 1s, right? The order doesn't matter. From that, we came up with these two equations, right? Now, you can reach from 0 0 to AB, or the vice versa. You can empty the piles if a valid solution exists for these two equations. And how does a valid solution exist for these two equations? Firstly, these moves cannot be negative. So xy has to be greater than equals to 0. And then there cannot be fractions. You cannot perform, let's say, some half number of moves here, right? So they have to be whole numbers. In a way, they have to belong to the set Z, right? If you remember from your school days. And these are just conditions you can derive from the equation. So I was just trying to solve this equation using the system of linear equations method. So pretty simple, right? So just these are the conditions that we have to do. So I hope you understood the explanation, right? It was pretty straightforward. And if you understood the explanation till now, please comment understood in the comment section of the video at the moment. So now the next thing I'm going to do is I'm going to show you the code. So let's just go through the code then. Okay, so the code is pretty simple. Like, we take the input for each test case, right? So here, first here is the test case input. For each test case, we are calling the solve function. And the solve function, it takes the input for a, b. And then, first condition, 2 into a minus b, is it divisible by 3? If it is divisible by 3, we are going to calculate y. Then y has to be non-negative. If y is non-negative, then only we move ahead. Y is non-negative, and then we first check if b minus y mod 2 is not equal to 0. That is, the b minus y is actually even or not, right? So that this was the second condition, right? If it is the case, then I'm going to calculate x. Then x has to be again non-negative. So x has to be greater than equals to 0. If everything is fine, that is x and y are valid, that is they are a whole numbers. Simple, right? So ye puri Ramayana yahi hai, like, we are reaching effectively here that x and y are valid whole numbers. Then we print yes and return. Otherwise, if none of this leads to you to anything a valid x and y, then you can just print no. Time complexity, this is just a constant time if checks, so order of 1. And since we will have to do order of an operation for every test case, order of t will be the total time complexity, which will be 1e5, right? So I mean, yeah, that's that about this question. I hope you got something out of this video. If you did, please like the video, and I'll see you in the next one.